Chapter 8. What counts as a harm? In Chapter 7, we asked the question of what counts as a design problem, and we looked at some problematic design choices. And in that chapter, we also mentioned that what we were concerned about was the harm to users. In this chapter, we want to talk a little bit more about harm and what counts as a harm. Again, this really all goes back to Chapter 6 in some way as a way of raising awareness when we're making design choices in engineering. So it's about being able to recognize or to think about or look at engineering decision making from a number of different angles. So I want to talk here about unprovoked harms. In the past, we've talked about provoked or error provocative harms, but it's not always the case that a design solution or the design harms simply because it's an error provocative design. Sometimes designs harm because we have to make choices and trade-offs in our design solutions. So let's go over just two examples. Talk about the clutch pedal. So your textbook mentions the clutch pedal on a car, and the idea that the author discusses how the clutch pedal was so designed such that it would interfere with its proper use. Now, one could say that's a design flaw with the pedal, but it's also possible to drive that car. It just depends on the individual. So while there has to be a trade-off in terms of how you can fit the clutch pedal in with the other pedals, there is a moral aspect to putting in a clutch pedal that might cause your foot to get slightly stuck or for the pedal to get stuck and so forth and so on. Probably a better example of a non-provoked error or a non-error provocative design is the airbag issue. We think about designing an airbag, it's not that airbags necessarily provoke errors on the part of the user. I mean, if we think about it, airbags are safety devices which are usually deployed because someone else has made an error. Either the driver's made an error in terms of the way they've driven the car or someone has hit the driver. Either way, it's not a problem with the airbag itself that causes a design problem, or can cause, in this case, a harm is what we're focusing on here. So if we think about what happens in the design of an airbag, we note from the text that there are multiple solutions and every single one of them is value laden. So let's assume you were designing one of the first airbags. The question, of course, is how would you design that airbag to deploy? How big would the airbag be? How fast would the airbag deploy? What would the angle at which the airbag deployed be set at? So there are a number of considerations. So the average height, weight, male, female of drivers and not the general population. So is that what we're looking? So we say, well, is it the average of drivers or the average of the population as a whole? So if we know what the average weight and height of males and females in a society is that what we should base our airbag dimension on? Or is it just of drivers? What about the average height of males, the average height of females? Notice that if I choose the average height of males, that means some males who are taller won't fit into that, and some that are shorter won't fit into that average. The same thing goes with females. So now the question is, which one am I more concerned about? The average, or am I worried about what happens to those at the top end or the bottom end of height or weight? And the same thing goes with females. Am I worried about what happens in the average height or weight to females? The top end or at the bottom end or in that big middle? Maybe I should be concerned with who's most likely to be driving. So if men are more likely to be driving than women, then should I skew my numbers towards males? And then again, it still brings up the question, should I skew it towards average males, above average males, below average males? That doesn't seem to make a whole lot of sense, but it is a decision I have to make. But we say, well, wait a minute, that's not fair either. What if the driving is 50-50? If women drive just as much as males, well, now I'm back to my original problem. What's most likely to be the cause of an accident? So maybe what I really want to do is say, look, those who cause accidents are more morally culpable for their action, and I shouldn't penalize the people who are generally in accidents. So is there an average height, weight, male, female of those in accidents who are affected by accidents? Most likely to be the victims of an accident. Should I be worried about the person who's the victim, or should I be worried about the person who causes an accident, or some combination of both? Because those who cause accidents and those who are victims of accidents are the ones that are going to need the airbag, as opposed to just people in general who drive and don't ever use the airbag, or the airbag is not necessary because they're not in an actual crash. But notice that all of these things bring up value judgments, whether we think about it or not. If you choose the average, you're saying something. You're saying, look, what I'm concerned about is a utility calculation. It's about whether I can get the most or do the most good for the most people. And I'm willing to sacrifice the others. I'm willing to say that I can't actually account for in my design those who might be a lot taller, a lot bigger, those who might be a lot shorter, a lot lighter. And so these things all become value judgments. And so the harms that we cause aren't necessarily provoked. It's not to say that the engineer intends to do wrong. They want to harm people. It's just that these are the sort of moral trade-offs that we make when we're doing design, which just shows, of course, that our designs are not morally neutral. So in this case, as the book says, no matter what our choice, we provide greater safety for some at the expense of others. And the criteria for who falls into each of those two groups will reflect a value judgment we have made, consciously or not. So again, here in this chapter, we're attempting to just raise your awareness of how these sort of value judgments sort of filter into design solutions. And of course, in this case, then, what types of harms we allowed. So remember, way back in the course, we talked about harm in terms of unnecessary harm. So it's quite possible that in these sorts of examples, we're talking about necessary harms. It's necessarily the case someone is going to be harmed. We can't make an airbag that is, or at least, I guess not yet, can we make an airbag that completely sort of molds itself to the person driving the car. Maybe as time goes on, that's what one of you as an engineer will do. You'll find a way that these are no longer issues. And then the only moral choice you'll have to make is between actually protecting people or not protecting people, which seems to be a pretty easy moral decision to make. Artifacts and sustainability. Another notion of harm is the notion of sustainability and environmental sustainability. So this, I think, is becoming more and more prevalent in engineering practice. People are starting to think of what happens to the things that I create. Is this a sustainable sort of product? So we want to consider not only what is made, but how it's made. And so we've mentioned this in previous chapters in the book, but our consideration shouldn't just be on whether I've got a good design, whether that design's realized in an artifact. We have to ask questions about how it's going to be realized in an artifact. So we have end of artifact life questions. Can this device be recycled? Can it be remanufactured? Some companies tout the sort of ability to recycle or the amount of recyclability of their products. Apple products, for example, their laptops made out of aluminum. The aluminum is recyclable. The glass is recyclable. They don't use certain chemicals in PCBs. The other gold and wire and copper that's used, all of that can be recycled from their laptops and their computers. So this is becoming something that is also a form of promotion for companies. But it's something that also engineers should be considering. Can this be recycled or can it be remanufactured? Can it be used in some other product when the artifact reaches its end of life? Throwaways. Again, a sustainability question. We can look and see here that we've got a number of examples of throwaways. When we create things like toys for McDonald's Happy Meal. See, I've got a little image here of a toy that my son recently received from McDonald's. And I say, well, this is nice, this is cute, this is promoting the Super Mario Kart. And so that's good for promotion and kids like it. But the truth is, how much or how often will this be used? Is this something that's just going to end up in the garbage? And how much or what types of resources were used, right? This is plastic. Plastic comes from oils. So we have to increase our oil production, or we have to use more and more oil to produce this stuff that is basically a throwaway. The same thing goes with Keurig. For those who have a Keurig coffee maker, these are extremely convenient, but what happens to all those little cups that are only used once? And you see now even that engineers have come up with new forms of the Keurig cup. Recyclable cups that can be used over and over, that are made of wire mesh, choosing different materials. But again, once you choose those materials, that brings in different mining. Right now we need more aluminum, or we need more steel, or we need more stainless steel, or whatever we're using for those cups. And these bring in those sorts of questions. But the big question here is the notion of a throwaway. Is this device repairable? What type of raw materials is it using? And what's the environmental impact of this device from its production? So we have oil production for plastics. We have the use of raw materials for the Keurig cups, but then the question of where do we put the used cups if they can't be recycled. All of these things become an issue, whether you're making artifacts that are simply disposable or whether they're for the long term. There's, of course, the potential for conflict. We can have harms when we look at, and we've mentioned this before, the engineer as professional versus the engineer as employee. So there's planned obsolescence, right? So as a professional, you might say, I've designed this product to as a solution to some problem. On the other hand, companies may want that device to be obsolete in a certain amount of time, right? You don't want certain objects that are going to last many, many years, because that means people aren't going to come back and buy more. And so the question is whether as an engineer, as a professional, you're recognizing your obligations versus those as an employee. If I know this device that I'm creating is going to be obsolete in a year or 2 years, which means it's going to use more resources, which brings up issues of recycling, manufacturing, and so forth, then this brings up moral issues. Whether or not you should have actually designed the product that way, whether you can in good conscience work for a company that asks you to have something that will break down after a certain amount of time, or using parts that you know are likely to wear out in a fairly short time, and then imposes a cost on the consumer, imposes a cost on the users of your designs. And of course, cheaper production means greater profit margins. So the question, of course, for an engineer is, where will this be produced? How will this be produced? And sometimes if you step outside your professional responsibilities as an engineer and go to an employee, so a number of engineers, I have family members who are engineers who moved from the actual design facets of engineering to the management facets. And so now you're making decisions that really aren't engineering ethics decisions, but are really more social decision making. Right? What kind of workers, or what workers, where are we going to use? Workers from where are we going to have manufacture our products? Is this something we're going to offshore to China? And are the environmental and workers' rights respected in those other countries where we produce goods? So there's a potential for conflict for what we as an engineer, or you as an engineer, I should say, have your professional moral responsibilities versus those that you might take on contractually, those as engineers, employee. Missed signals. So here's another sort of harm. This is when the artifact doesn't tell you things that are important for the user to know. So artifacts that present no information to the user when he or she most needs it. And these are a number of examples the book brings up. To go over some of these, useless information. For anyone who's ever had a computer error message knows that a lot of times these things are completely baffling. What is this error? It doesn't say exactly what the error is. It doesn't give us an easy access to find it. I suppose with a little Googling, I go in there and maybe find someone who's actually written about this. And generally they've written about it because it's a response to so many people having this error and not knowing what it is. So computer error messages are a sort of perfect example of useless information that an artifact can give to us. A program or a computer gives us information, presumably to help us, but in actuality it doesn't do anything for us. So it may not harm, but it leaves us in a state of harm in essence, right? Because now I've got a problem with my computer or with my program and I have no clue what to do. Ambiguous information, sliding doors and security. So sometimes the design of an artifact or even the layout of the artifact can affect harm or can impose harm. So here's an example. The author gives the example of sliding doors at a store. And this one has actually happened to me as well. This you can obviously see as a Target store. Target has sliding doors. When you run into a Target store, you're going in and you see sliding doors, you're thinking, I have nothing to worry about. In this case, and the Target stores all have these double sliding doors. So you go in thinking, I could be watching my young son. I can be carrying things with me. I can be thinking about what I'm going to do. I'm looking at a list. But right inside are also these sensors. And so it's been the case where I've actually had to stop and almost hit into a pole. But it's ambiguous, right? Because everything about the design is saying, come in, don't worry about it. I've got the door, carry your goods, bring your kids, do what you need to do. And yet, at the same time, this can cause error on the part of users, right? It can cause harm just because of the layout. Now, again, this might not be the engineer's problem. The sliding doors work fine. The sensors work fine. It's the combination of the two. So maybe the engineers need to be aware of where they're putting their sensors more so than where the doors are. Other bad signals. The shoulder harness in a car. The example given in the book about the strained shoulder harness seat belt in the author's car. I had a similar experience with the Toyota Tercel. It was funny, people would get in my car, they would see the shoulder strap, they put the shoulder strap over in the passenger seat, and then I would still have to tell them to buckle up. And they said, well, no, I have just buckled up. I said, no, there's a second belt that goes across your waist. And so this one gives you no indication that there's more than one thing that you have to do. You have this harness that's up, it's connected to the roof, it moves as you get into the car. You think to yourself, I'm all ready to go. And then I would be constantly reminding people who would drive with me that they had to put on the other belt buckle. Shower faucets. And this one, interesting, as I read this, it was one that I'd often thought about and never really viewed it as a design error, although maybe I had viewed it as a design error, but I'd also just viewed it as an annoyance, right? This was something that caused me harm in very loose sense of harm, as an inconvenience. But when you go into a shower where it's almost impossible to figure out how to turn on the water. Now, we've had a lot of experience for a lot of years with showers. And I think most of us have experienced different types of shower mechanisms. But there are some that are truly just baffling. When you go and you just cannot figure out how you're supposed to get the shower to operate, where the hot and cold is, how you adjust things. And the fact that you actually have to post a guide to turning on the shower says that, look, maybe it's just simply a bad design, and it's a bad design that causes harm, right? So it doesn't provoke error, because in this case, you don't get an error right off the bat. You just can't use it. So again, though, this is a sort of harm. If I go in and do get it to work and end up burning myself because I don't know how far to go for hot or cold, or which way is hot or cold, if it takes time out of my day such that I'm frustrated and I end up late for my meeting or whatever when I'm staying at a hotel and trying to get somewhere because I can't operate the shower, then this all does have a form of harm. Again, it's not terrible harms, but it's harms that could be avoided with better design. And so even something like this constitutes a harm when you have to go to the level of posting steps on how to turn a shower on. So there are 3 problems with artifacts. One of those 3 problems, we cannot tell how something works by looking at it. In many cases, the sort of hallmark of a good design is that I can look at it and sort of get an intuitive sense of how it's supposed to work, that there's a form that follows function, that when I look at the shower, I can see exactly how to turn that on, or it gives me some clue in the design how it's supposed to work. We bring different histories to artifacts that interfere with artifacts that work differently than history has primed us to think they work. So sometimes we have artifacts, this again going back to sort of the Cadillac trunk example. We bring history of objects with us, and an engineer can't ignore the fact that most objects, most artifacts have a history. It's the sort of lucky engineer that gets to start from scratch with something that's completely new, because that engineer gets to sort of redefine the space in a certain way. What a number of people noted, for example, with the first iPads. People looked at an iPad, it was, gosh, I don't know what to do with this, or who's going to need that? Who's going to want to have something like a mobile device? And now we can see there are tons of different iPad-like devices out there. But it turns out that those engineers had an advantage. The previous sort of touchscreen computers basically went off a Windows sort of model. This one brought in a whole new interface. And so people had to be shown how to use it. But they didn't come in with a lot of preconceived notions. Maybe their iPhone or their Galaxy phone or their HTC phone gave them some hint as to how to pinch and move and swipe. But the device itself, one, was intuitive because it was touch and it was meant to be used with your finger, like you would expect to point to something and work it. But it also had a number of features that you really just had to learn. So you didn't bring a history. With other objects, that's not the case. Trunk lids and showers and other everyday objects do have a history. And if the engineer ignores that, they can cause harm just in the fact that they've ignored the history of an object. And we bring different bodies to artifacts. So, of course, just like the car example, the airbag example, or the clutch pedal example, we also have to think that these artifacts are not used by people of the same shape and size. Our bodies are different, and therefore the way in which we interact with artifacts is going to be different. And engineers should be aware of that, because when they're not aware of that, they can inadvertently cause harm, even though they don't intend to. It's just that's what happens when you don't take that into consideration. So let's look at a few other harms. What I want to emphasize here is that engineers should not focus on the size of the harm. So while of course we can make moral distinctions, that it's more wrong in some sense to hurt someone in a substantial way versus to hurt someone in a minor way. It really is the case that engineers should be focusing on just minimizing harm altogether. There's no, to use sort of a cliche, there's no job that's too small. So whether you're designing a toothpick or whether you're designing an airplane, anywhere in between there can be harms of various sizes. And the idea should be that when you can, you should minimize those harms. So there are several prominent examples of major harms, which is why in some cases we don't really need to focus on these. I think most people are aware of the different types of major harms. And I'll just go over a few examples just to remind just how easy it is to find these sorts of examples. So take a look at the Hyatt Regency example in Kansas City. Picture here on the left was the pre-collapse. So the Hyatt Regency had this walkway, had designed inside the suspended, nice, pretty walkway, and it turned out that the design was so poorly done that that walkway ended collapses. So this is looking at the same picture from a different angle. So from the other side, you can see that the entire walkway collapsed with several people being injured and killed. So this is a major example, right? When we look at this, we can say clearly there was a moral wrong, there was a harm done. This is something that should have been avoided, that should have been anticipated by engineers. The Big Dig in Boston. For those who aren't familiar with the Big Dig, it's where Boston was putting an underground road. They were expanding their freeway in the city using almost like a car or a train under the ground, but they were using it for cars. So there was a huge dig. And it turns out that due to design errors, that there was a ceiling collapse that caused death and injury in the Boston case. So again, an obvious example of harm due to faulty engineering. Flood walls in New Orleans, there was a lot of criticism with Katrina that the flood walls were not properly designed, that the Army Corps of Engineers should have done or anticipated more problems in terms of how much water and pressure and what would be needed if a larger category storm came into New Orleans. And the interstate bridge collapse, which many of you will probably remember. Again, a huge engineering problem, partially a maintenance problem, but also just an engineering mishap, right? We can find these sorts of examples all over the place. So what are our conclusions about harm in engineering? One, engineers must trace out the design choices to see where it will lead. So the idea is that you must look at your design and see who's going to use it, what different people are going to use it, what sort of history are they bringing in, sustainability questions, recyclable, whether it's recyclable or remanufacturable. All of these things have to be taken into account when making a design choice. Materials, repair, end-of-life issues need to be considered. And all choices can introduce harm. Now again, these are not necessarily error-provocative designs. These aren't harms that are necessarily just because you've created an artifact. The artifact itself provokes harm. But we should be aware that every time we make a choice, there's a potential for harm in our designs. And so we want to minimize those harms, even ones that in some sense might be necessary. The airbag example is one where it might just be the case that it's impossible to make a perfect airbag. But we still should recognize that any choice we make in those cases, and cases like that, are going or have the potential for introducing a harm to individuals. So all choices in this case are moral choices in engineering.